In this video, we will introduce the notion of limits of functions of two variables, and this is found in section 14.2 of our text. So we will start with the example where we're asked to compute the limit as xy approaches the point 0, 0 of the function sine of x squared plus y squared over x squared minus y squared. And what we've been given is a table of values for this function for a variety of choices of x and y as x and y are approaching 0 from both the positive and negative directions. And if you look at this table of values, it looks like regardless of which direction you're using to approach the point 0, 0, that the values of the function are getting closer and closer to the value of 1. So it looks like we should guess that the limit of this function is 1. Now let's compare that to the next limit. Again, we're approaching the point 0, 0, this time of the function x squared minus y squared over x squared plus y squared. And what I want to point out this time is that if we fix x to be 0, then it looks like the function is approaching the value negative 1. However, if we fix y to be 0, then it looks like our function is approaching the value positive 1. Or if we consider approaching the origin along the line y equals x, then in this case it looks like our function is approaching the value 0. And so as you might guess, in this case, because we don't get one unique answer, this suggests that the limit of this function does not exist. All right, so let's get into the details here. First, recall that back in our Calculus 1 days, we said that the limit as x approaches a of a function f of x is equal to the value L if, essentially, our function is getting closer and closer to the number L as x is getting closer and closer to the value a, approaching from both the right and the left. So here we see two options. And the first, in option A, we have the function x squared minus 4 over x minus 2. And notice that as x approaches the value 2 from both the right and the left, our function is approaching the y value 4. And so we would say that the limit as x approaches 2 of x squared minus 4 over x minus 2 equals 4 because we got the same y value as x approached a from both the right and the left. On the other hand, in option B, the function absolute value of x minus 2 over x minus 2. Here, as x approaches 2 from the left, we see that we're approaching the y value negative 1. And as x approaches 2 from the right, we see that we're approaching the y value positive 1. And since we ended up at different y values, we would say that the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2 does not exist. And so the key here, right, the fact that we had to approach from both the right and the left, really what we were doing is we were just looking at all possible ways x could approach the value a along our domain. All right. So what about in two variables? Well, we're going to say that the limit as xy approaches the point AB of the function f of xy is equal to the number L if our function f of xy is getting closer and closer to the number L as xy gets closer and closer to the point AB along any path in the domain of f. The key here, here's a picture of our domain. And we've got to consider how the ordered pair xy can approach the point AB along any possible path in the domain. So it can approach along a straight line, it can approach along a parabola, it can approach along any kind of curve that we can possibly imagine. But in order for the limit of the function to exist at the point AB, then regardless of how that ordered pair xy is approaching the point AB, we must get the same value for our limit. So what that tells us is if our function is approaching a limit L1 as xy approaches AB along a path C1. And our function is approaching a different limit L2 as xy approaches AB along a different path C2. If we get two different values for the limit, then that automatically tells us that our limit at AB does not exist. And so if we want to show that a limit does not exist, we need to find two different paths, a C1 and a C2, that are going to lead to two different limits, L1 and L2. So let's do some examples and see this in action. Here's our first example. Let's show that the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist. So our function in this example is the function x squared minus y squared over x squared plus y squared, and we are approaching the point at the origin, 0, 0. So one way to approach the origin is to approach along the x-axis, which is when y equals 0. And so if in our function we let y equal 0, we have the limit as x approaches 0 of x squared over x squared, which simplifies to the limit as x approaches 0 of 1. The limit of 1 is, of course, 1, and we're going to call that our first limit L1. Now next, let's approach the origin along the y-axis, which is, of course, when x equals 0. So if in our equation we let x equal 0, we have the limit as y approaches 0 of negative y squared over y squared, which is the limit of negative 1, which is, of course, negative 1. And we'll call that L2. So now we found two different approach paths. The x-axis led to the limit positive 1. Approaching along the y-axis led to the limit negative 1. And since we found two different limits, since L1 is not equal to L2, then that automatically tells us that the limit of this function does not exist. Let's do another one. Does the limit as xy approaches the origin of xy over x squared plus y squared exist? So here our function is the function xy over x squared plus y squared. And again, in this example, we're approaching the point 0, 0. So one way to approach 0, 0 is along the x-axis, which is where y equals 0. If we replace y equals 0 in our equation, we have the limit as x approaches 0 of 0 over x squared, which is the limit of 0, which is 0. Now, if we follow what we did in the previous example, we could try approaching along the y-axis as well, which is when x equals 0. But this time, if we replace x equals 0 in our equation, we have the limit as y approaches 0 of 0 over y squared, which is 0. Notice we got the same value for the limit. This is where we must be careful. Notice we are not done with this problem. It is not enough to assume now that the limit of the function is 0, not by a long shot. Because remember, in order for a limit to exist, we would have to check every single possible path approaching 0, 0. It's not enough to stop at just checking these two. And in fact, what happens if we decide to approach 0, 0 along the line y equals x? So if in our equation we let y equals x, we have the limit as x approaches 0 of x times x over x squared plus x squared, which simplifies to the limit as x approaches 0 of x squared over 2x squared, which is the limit of 1/2, which is 1/2. So notice, now we have found an approach path, a way to approach the point 0, 0 that led to a limit other than 0. So, since we found two different limits, then that is enough to stop and say that our limit does not exist. Keep in mind, we're only allowed to stop if we find two different limits. Here's another example you can try. The limit as xy approaches 0, 0 of the function x squared y e to the y divided by x to the 4th plus 4y squared. Now, the first approach region you always get for free. So maybe you'll start by approaching along the line y equals x. In that case, you'll have the limit as x approaches 0 of x squared times x e to the x divided by x to the fourth plus 4x squared. This becomes the limit as x approaches 0 of x cubed e to the x divided by x to the fourth plus 4x squared. Factoring out and canceling an x squared, we're left with the limit as x approaches 0 of x e to the x over x squared plus 4. Evaluating at x equals 0, we get the limit of 0. Now, we might want to be a little bit strategic about how we choose our next approach path. So one thing to keep in mind, we want to be able to combine what's happening in the denominator, that x to the fourth and that y squared. So in order to combine them, they need to have the same power, right? So you may then try to approach along the parabola y equals x squared. So if in our equation you replace y with x squared, you get the limit as x approaches 0 of x squared times x squared e to the x squared over x to the fourth plus 4x to the fourth. We can now combine what's happening in our denominator. So we have an x to the fourth e to the x squared over 5x to the fourth. Cancel the x to the fourths, and we're left with the limit as x approaches 0 of e to the x squared over 5. Substituting at x equals 0, we get the limit of 1/5. And since we found two different limits, we're able to conclude that the limit of our function does not exist. So keep in mind, the key is always to be able to find two different limits. And one trick is to kind of think about how you can combine those powers in the denominator. One final example for you to try on your own that's a little bit different is the limit as xy approaches the point 2, 0 of the function xy over 2 minus x plus y. So our function we see here. And what we want to be careful about in this case, we're not approaching the origin, right? This is the first example where we're approaching a different point, the point 2, 0. So we have to be careful that the approach regions we use do in fact include the point 2, 0. So you can still use your x-axis, that's no problem. And if you do, you'll get a limit of 0. But this time we're no longer allowed to use the y-axis because the y-axis does not contain the point 2, 0. Instead, we could try using the line x equals 2, since x equals 2 does contain the point 2, 0. And if you let x equal 2 in our equation, we get a limit of 2. Since we've now found two different limits, then we're able to conclude that the limit of the function does not exist. Great, that's all for our introduction into limits. Thanks so much. Bye.